Hi everyone! In this video we are going to start chapter 6, which is all about chemical reactivity and mechanisms. So first we're going to start off by reviewing enthalpy, entropy, and Gibbs free energy, and then we'll move into different types of mechanisms. So let's start with enthalpy. So you might remember that enthalpy measures the amount of heat released or absorbed by a reaction. Oh, let me change my marker color here. So this is assuming that we have constant pressure and volume. Now, the way that we symbolize enthalpy is with delta H. And if delta H is positive, that means that the reaction absorbs heat overall. This is also referred to as endothermic. And then if delta H is negative, that means that the reaction releases heat overall. And that's referred to as exothermic. So for example, if you've ever used an ice pack, where you have to kind of break apart the packet a little bit, you're breaking apart any seals in the packet and you're starting a reaction that is endothermic. So it absorbs heat from its surroundings and it feels cold to you because you're the surroundings. But if delta H is negative, that might be something like a combustion reaction where your overall energy is negative, so you're releasing heat from the reaction, so the surroundings will feel that heat as a result. Now, there are a couple of different ways you can calculate enthalpy, but we're going to stick with the easier way to calculate it. So delta H, or enthalpy, can be calculated using bond dissociation energies. And you can find these in table 6.1 of your textbook. And if I ask you to calculate delta H on a test or a quiz, I'll likely give you this table so that you don't have to go searching for it. So feel free to pause the video and pull out your textbook and find table 6.1 because we're going to go over an example problem next. Okay, so in our example problem, let's say that we have propane and it's reacting with bromine. And remember, bromine is one of our diatomic molecules, so there's two bromine atoms bonded together there. And then we add some energy in the form of light. So H nu tells us that we're using light. So H is Planck's constant, nu is frequency. And then after this reaction, we end up with this product and hydrobromic acid. So real quick, let's just name the other product. How would we name that product? So what is our longest carbon chain? Well, we have 3 carbons in a chain, so that would be propane. And then how would we name that substituent? Bromo. And which carbon is it on? The second carbon. So this would be 2-bromopropane. And bromine will be on carbon 2 no matter which way we number it, left to right or right to left, so that's easy. Okay, so now we're going to calculate the enthalpy for this reaction, and we're going to first figure out which bonds are broken in this reaction. And those will be endothermic. So if you break a bond, you need energy to break that bond. So we'll say that those are positive values. And then if the bonds that we make, those will be exothermic or negative, because once you make a bond, energy is released. Okay, so we're going to use table 6.1 to find the energies of each of the bonds that are broken and each of the bonds that are made. So first, let's try to identify which bonds are broken and which bonds are made. So let's look at propane versus the product 2-bromopropane. Now, originally at carbon 2, we had 2 hydrogens. And on 2-bromopropane, remember there's a hydrogen here that we're just not drawing because this is a bond line structure. So it looks like we had to break one of the carbon-hydrogen bonds on on propane in order to make the carbon-bromine bond on our product. So I'll use red highlighter for bonds that are broken. So I'll just highlight this down below, and I'll use yellow highlighter for bonds that are made. All right, now we also had to break apart our bromines in Br2 in order for them to join other molecules or other atoms. So we already talked about this bond in 2-bromopropane, the carbon-bromine bond, but we also had to make a hydrogen-bromine bond in the products. All right, so let's look up each of those bonds and their energies. So under bonds broken, let's write out H is bonded to a carbon that's bonded to another hydrogen as well as 2 methyl groups. And if we look in table 6.1, if you look in the middle column at the very bottom, we have a hydrogen bonded to a carbon, bonded to hydrogen, and 2 methyl groups. Okay, so let's use the units of kilocalories per mole. So in that column, it tells us that this bond, whoops, whoa, oh no, keep from current, there we go. It tells us that this bond is 95 kilocalories per mole. All right, the other bond that we broke was a bromine-bromine bond. So if we look in the third column of table 6.1, at the bottom we have halogen bonds. So if bromine is bonded to bromine, that energy is 46 kilocalories per mole. And you could do this in kilojoules per mole too, that's fine. All right, so now for bonds made. So we made a bond between bromine and propane. And the energy for that can be found in the third column of table 6.1 as well, kind of towards the top. So that energy is 68 kilocalories per mole. And again, that will be negative 68 kilocalories per mole because we're going to release energy when we make that bond. All right, and then the last bond that we made was hydrogen to bromine. And if you look in table 6.1 in the first column, kind of towards the bottom, you'll find HBr, and the energy of that is 88 kilocalories per mole. But again, that will be negative because we're making a bond which releases energy. Okay, so now we just add all of these numbers together. So delta H of the reaction is equal to the sum of all bonds, made or broken. All right, so let's start with our broken bonds. We have 95 plus 46. So those are positive numbers because we're breaking the bonds. So you need energy to do that. And then we're going to subtract 68 and 88 because, again, those are negative. All right, so this should give us an overall energy of negative 15 kilocalories per mole. So is this reaction exothermic or endothermic? Exothermic. And that's because we have a negative energy. So that tells us that energy is released from this reaction. Okay, so that's just a quick review of enthalpy. Let's quickly review entropy. So entropy measures the disorder or randomness of the universe. But you can also narrow this down to the disorder or randomness of a reaction or your surroundings. It kind of depends on where your frame of reference is. So let's just focus on the system, so our reaction for the time being. And entropy is symbolized with delta S, and then we'll just write system as a subscript. Now, if the entropy of your system is positive, that means that your reaction becomes more disordered. And then if delta S of the system is negative, that means that the reaction becomes more ordered. Now, you can predict the sign of delta S. Oops. Spelled that wrong. Oh. I think I'm thinking faster than I can write. Let's see, can predict the sign of delta S by counting out the number of moles of products and the number of moles of reactants and then comparing them. So for example, let's say we have more moles of products than reactants. That means delta S of the system is positive. So if you end up with more moles of product, your reaction becomes more disordered as it proceeds. Now, what if you have fewer moles of product then reactants. That means that delta S of your system, or the entropy of your system, is negative. So the reaction is becoming more ordered as the reaction proceeds. Now, what if the moles of the products equals the moles of the reactants? Then it depends on the freedom of motion of your reactants and products. So for example, if you go from, let's say, solid to liquid, then your reaction is becoming more disordered because liquid atoms can actually move around a little bit. Solid atoms are pretty stuck in place, so that's more disordered. So delta S would be positive. And then if you're going from liquid to solid, for example, so in the opposite direction, then your reaction is becoming more ordered. So it would be negative. So let's look at a couple of examples and see if we can predict the sign of entropy for a reaction. So in our first example, we're going to look at a reaction between something called a diene. So this is basically a molecule that has two alkenes in it. And it's going to react with a pretty simple alkene. And this is going to form cyclohexene. And this is actually a pretty well-known reaction that we'll talk about later on. But let's count the number of moles of the reactants and the number of moles of the product. So how many moles of reactant do we have? 2. We have 1 mole of each reactant for a total of 2 moles. And how many moles of the product do we have? Just 1. All right, so since we have more moles of reactant than product, is this going to be a negative entropy or a positive entropy situation? Or another way to ask that is the entropy increasing or decreasing? So is this reaction becoming more ordered or disordered? This is becoming more ordered, which means that entropy is decreasing. So the disorder is decreasing. So in this situation, delta S of the system is negative. Okay, let's look at another example. In this example, we have the following molecule, and this is actually going to break apart. So the bond between oxygen and the next carbon is going to break. And this is going to give us let's see if I can draw this correctly. One, two, three, four, 5. There we go. So is the product more ordered or more disordered than the reactant? It's more disordered, right? There's more freedom of motion. Whenever you have a ring in your molecule, that's going to create less freedom of motion. So the atoms can't move around as much in a ring. Okay, so if the product is more disordered than the reactant, is the entropy positive or negative? Positive. So disorder is increasing, which means entropy is increasing, so that is positive. All right. So I think we'll stop there for today. We got to review enthalpy and entropy. Next time we're going to go over Gibbs free energy and we'll look at some energy coordinate diagrams or reaction coordinate diagrams. So I will see you then.